Another hand computation in determining the load distribution in bridges is Courbon'S method. This approach doesn't use curves or graphs, so it is more computational and accurate than Pigot's method. Welcome to Bridge Engineering. A simple span bridge of 20-meter length has three main girders, which are spaced at 2 meters. A moving point load of 60 kilonewtons crosses the bridge, and it is placed 1 meter to the right of the center line. We are to determine the maximum bending moment in girder C at midspan. Illustrating the data provided, the simple span bridge is 20 meters. The cross-section shows the three girders A, B, and C, and they are spaced at 2 meters. Taking into account the locations, the center line is aligned with girder B, locating girder A at -2 and girder C at +2 meters. The load, as stated in the premise, is placed 1 meter to the right of the center line. There are two parameters required to solve for the moment. One is the ordinate of the influence line. For the simply supported bridge, the maximum moment at midspan occurs when the load is applied at midspan. For the influence line, the maximum moment is computed with A times B upon the length of the bridge. A and B are the bridge distance from the location of the load. With A being the same as B, the maximum moment is then half of L times L over 2 divided by L. This is simplified as L over 4. And from the problem, the moment is 20 upon 5, which gives 5 meters. This is the influence line ordinate, one of the necessary parameters. The next step is for the load distribution, where we use Courbon'S method. The example has a load of 60 kilonewtons, which is to be distributed across the three girders. Courbon'S load distribution formula is shown, where W is the total load on the bridge, N is the number of girders, I is the moment of inertia of the girder under consideration, E is the eccentricity of the load from the center line, X is the distance of the girder from the center line. R from the equation is the reaction of the girder, and this shows how much load the girder carries. A simpler equation is also provided for girders with uniform sizes. The equation as shown includes the same parameters like W for total load, N for the number of girders, E for eccentricity, and X for the distance of the girder from the center line. Placing the numerics into the equation, we consider 60 kilonewtons for W, N is 3, and E is 1 meter. The denominator is the summation of the square of the distance of the girders. This is the square of -2 plus the square of 0 and the square of +2, which is then simplified as 8. Plug these values into the equation, giving R of girder C as 60 over 3 times 1 plus 6 of 1 times 2 all upon 8. This is 50 kilonewtons. At this point, we can see that girder C carries most of the total load of 60 kilonewtons. Now we can finally determine the moment of girder C from the reaction of girder C of 50 kilonewtons and the influence line ordinate of 5 meters. The moment at C is 50 kilonewtons times 5 meters, which is 250 kilonewton meter. This is the answer to the task. If we compute for the moment of the total load, it is 60 by 5, which is 300 kilonewton meter. Comparing these two moments, we can see that girder C takes most of the total load. Using the same bridge setting, try looking for the maximum bending moments at midspan in girders A and B. The procedure is similar with the example. You are to come up with the reaction at girder A as negative 10 kilonewton and at girder B as 20 kilonewtons. Good luck!